Assalamualaikum warahmatullahi wabarakatuh and good day to all of you. So for chapter number 5, part number 2. So we will discuss about axial flow compressor in terms of stage losses and also efficiency. Okay, for stagnation losses, stage losses, relationship and also efficiency. The schematic diagram shows the arrangement of blade rows. So we have previous stator blade rows, rotor blade rows, and also stator blade rows, where the condition number 1 is the inlet of the rotor, condition number 2 outlet of the rotor or inlet of the stator, and condition number 3 represent the outlet of the stator. And the second figure shows the HS diagram for the compression process in a compressor stage. So we have a lot of points involved with different type of pressure: static pressure, stagnation pressure, and also relative stagnation pressure. And in the graph also we'll have what we call the term for kinetic energy in terms of relative velocity and also absolute velocity. Okay, in terms of relationship, for the actual work performed by the rotor on unit mass of fluid, we have equation number 1, where actual work delta W equal to rate of work done W dot divided by mass flow rate M dot equal to stagnation enthalpy at the outlet of the rotor H02 minus stagnation enthalpy at the inlet of the rotor. Okay, so if you consider Euler equation, delta W will be equal to U multiplied by Cy2 minus Cy1. Okay, so for the value for Cy2 and also Cy1, in order to obtain the value of Cy2 and also Cy1, we need to analyze the velocity diagram for the rotor at the inlet of the rotor and also at the outlet of the rotor. Okay, at the stator, we know that the relationship, special relationship for the stator, the stagnation enthalpy at the inlet of the stator equal to the stagnation enthalpy at the outlet of the stator. That represented by equation number 2. So substitute equation number 2 into equation number 1. So the actual work also, we can obtain the value of actual work delta W equal to stagnation enthalpy at the outlet of the stator H03 minus stagnation enthalpy at the inlet of the rotor H01, represented by equation number 3. Okay, so the value of delta W actually refer to the actual work that need to supply to the compressor H03, and the enthalpy value that represent, if you look at HS diagram, H03 is stagnation enthalpy at 0.03 and H01 stagnation enthalpy at 0.01 as shown in the HS diagram. And the line shows the actual process of the compression for the compressor stage. Okay, for the reversible or minimum work required to attain the same final stagnation pressure as the actual process, where P03 equal to P03SS, if we refer to HS diagram, 0.03 and 0.03SS actually located on the same constant pressure line as shown in the HS diagram. Okay, so for the ideal case for the compressor, actually the best performance for the compressor need to have the minimum value of work that needs to supply to the compressor. That's why we consider delta W minimum, where in terms of formula, in terms of enthalpy difference formula, delta W minimum actually equal to H03SS minus H01. Okay, if you refer to HS diagram, enthalpy at 0.03SS and also enthalpy at 0.01. And the line, the vertical line, represent the ideal compression process for the compressor. So this value will give you the minimum what I call work that need to supply to the compressor. Okay, so if you look to the HS diagram, the call the delta W minimum equal H03SS minus H01 also equal to H03 minus H01, the actual enthalpy difference, minus H03S minus H03SS minus bracket H03 minus H03S, represented by equation number 4. So we can look clearly, the value is the same if you refer to the HS diagram. Okay, so the term for H03 minus H01, if we refer to equation number 3, the term actually refer as the actual stage work delta W. And the second term, H03S minus H03SS, actually the enthalpy difference that related with losses in the rotor. And the term for H03 minus H003S, actually the term that related with losses in the stator of the compressor. Okay, so for the first term in equation number 4, if we refer to the work done equation number 3, so H03 minus H01 actually equal to delta W. And the term of H03S minus H03SS actually refer to the total pressure loss for the rotor, delta P naught rotor. And H03 minus H03S actually equal to delta P naught in the stator, total pressure loss in the stator. And we will get this equation after we implement the enthalpy and Bernoulli equation for the enthalpy difference in equation number 4. The equation that involve such as the basic equation for the stagnation enthalpy, what I call the basic enthalpy relation that involve with temperature, and also the Bernoulli equation. So if you look in the equation for the stagnation enthalpy and also the Bernoulli equation, the equation will involve with C value, which is referred to the absolute velocity value. So from this value, we can manipulate and we will get the relationship in terms of total pressure loss for the rotor and also total pressure loss for the stator. Okay, so in order to obtain total to total efficiency equation for the compressor, divide equation number 4 with equation number 3. So we will get the formula for total to total efficiency, what I call for the compressor. So we will not have what I call the formula for total to static, because the energy, the kinetic energy that produced from the compressor will fully utilize in the gas turbine. Okay, so in the gas turbine, if you consider what I call the fluid kinetic energy from the compressor, the fluid kinetic energy of the compressor will fully utilize in the combustion chamber in a gas turbine engine. So that's why we only have total to total efficiency for the compressor stage. So the total to total efficiency for the compressor stage equal to delta W minimum divided by delta W, which is referred as the actual work, equal to 1 minus delta P naught for the rotor plus delta P naught for the stator divided by H03 minus H01, represented by equation number 5. Okay, so by using equation number 5, we can determine the efficiency of the compressor stage. Okay, now we will discuss about how to determine the stage losses in terms of delta P naught for the stator and also delta P naught for the rotor. Okay, last time we already learned about the compressor cascade performance that introduced by Howell 1942. So Howell introduced the graph for compressor cascade performance as shown in the slide. So we have the relationship in terms of deflection angle and also total pressure loss coefficient omega bar versus incident angles. So if you know incident angles, we can determine the total pressure loss coefficient. Okay, so now if we look at the equation of the omega bar, so in the equation we will have the term for delta P naught, total pressure loss. So we can manipulate the value of omega bar to obtain delta P naught value for the stator and also for the rotor. Okay, so from the graph of Howell 1942, we can estimate losses in the compressor stage by determining the value of omega bar and then manipulate or rearrange the equation for omega bar. We can determine the value of delta P naught for the stator and also for the rotor. And then we substitute the value of delta P naught for the rotor and also for the stator that we obtain into the equation for total to rotor efficiency mu Tt, where mu Tt equal to 1 minus delta P naught for the rotor plus delta P naught for the stator divided by H03 minus H01. Okay, so for the Howell, we need to know that for omega bar equation, the term for C1 in the omega bar equation actually represent the absolute velocity at the inlet, C inlet. Okay, so C1 in the equation of omega bar actually represent the value of absolute velocity at the inlet, whether for the stator or for the rotor. Okay, let's say we have incident angle for the stator. So from the Howell graph, so we just draw the vertical line, intersect with omega bar curve, and then we can obtain the value for omega bar, where omega bar, because we use incident angle for the stator, so we'll get omega bar for the stator, which is equal to delta P naught for the stator divided by half rho C inlet for the stator square. And then if we have the incident angle for the rotor, draw vertical line, intersect with omega bar curve. So we will obtain the value for omega bar for the rotor, where omega bar for the rotor equal to delta P naught rotor divided by half rho C inlet for the rotor square. Okay. Okay, so if we look at the visual diagram for the inlet of the rotor and also inlet of the stator, where the inlet of the rotor represented by condition number 1, inlet of the stator represented by condition number 2, as shown in the figure. So C1 in the visual diagram is represent the value of C inlet for the rotor. That's why we have omega bar rotor equal to delta P naught rotor divided by half rho C1 square. And then from this equation, rearrange the equation for omega bar rotor, we can obtain delta P naught for the rotor, total pressure loss in the rotor. And if you look at the second velocity diagram, C2 represent the C inlet for the stator. That's why for the equation omega bar stator, the equation also equal to delta P naught for the stator divided by the half rho C2 square. Okay. And for the from the omega bar stator, rearrange the equation, we can obtain the value for delta P naught for the stator, total pressure loss in the stator. Okay, so when we obtain the value for that delta P naught for the rotor and also for the stator, we can substitute this value into the total to rotor efficiency equation. Okay. So part of the parameter that involves total efficiency already solved by using this method, by using the compressor cascade performance graph that suggested by Howell 1942. So the term for H03 minus H01 in the total efficiency equation can be solved by referring to the Euler equation, where the H03 minus H01 actually equal to U Cy2 minus Cy1, where the value of U, Cy2 and also Cy1 we can obtain from the velocity diagram. Example 5.1. Figure 1 shows the general velocity diagrams at the rotor and stator inlets for a compressor stage. The data conditions of the compressor, rotor and stator inlet are stated in the table 1. The compressor rotor rotates at blade speed 100 meter per second and causes fluid flow through the compressor rotor with constant axial velocity at 50 meter per second. The characteristics of the compressor blades are shown in figure 2. Can be used to estimate the performance of the compressor. Take air density rho equal to 1.225 kg per meter cubic. First, question A, draw the velocity diagram by using a graphical approach. State all the vector components values including the angles. Question B, by referring to the compressor blade characteristic in figure 2, determine the total pressure loss delta P naught in the rotor and stator. Question C, if equation 1 is used to determine efficiency of the compressor, calculate the total efficiency of the compressor. Okay, solution for example 5.1. So in this question, you need to draw a velocity diagram and state all the components. So you need to use ruler and also protractor in order to determine what I call the angle and also the magnitude for the vector component in the velocity diagram. So first you need to decide your own scale before you draw the vector or velocity diagram. Okay, first we look at the table given in the question, where the table in the question gave you the information in terms of inlet blade angle, inlet absolute flow angle, and also inlet relative flow angle for the rotor and also for the stator. So first we need to identify the value given is related to which called parameter symbols. Okay, inlet blade angle for the rotor represented by alpha 1 prime. Inlet blade angle for the stator represented by alpha 2 prime. And the inlet absolute flow angle for the rotor alpha 1. Inlet absolute flow angle for the stator alpha 2. And for the inlet relative flow angle for the rotor beta 1, and for the stator is referred to beta 2. And the value for alpha 1 prime, alpha 2 prime, alpha 1, and also beta 2 already given in the table. So from data given, we need to manipulate the value to draw the velocity diagram. Okay, so we know that the blade speed in terms of magnitude is 100 meter per second, and the direction of the blade speed u vector is in horizontal direction. So by using what I call the vector principle, okay, so before that we know that the axial velocity component is constant, so thus we conclude that cx value equal to 50 meter per second. So we can draw two limit line for the axial velocity component cx. Okay, by using the vector principle, we can draw the what I call the C2 vector, because the C2 vector, C1 vector, where C1 vector in terms of flow angle alpha 1 already given 25 degree. Okay, so from the endpoint of the U vector, we can measure the angle and just draw the line according to the angle. So the line that intersects with the I call the upper limit of axial velocity is referred as the line for the vector C1. Measure the line, so we will get C1 equal to 55.4 meter per second. Okay, and then complete the vector triangle. We will obtain the line for the vector W1. Okay, so measure the W1 distance by the ruler. So we can obtain the velocity for W1, where the value for W1 equal to 91.2 meter per second. And also we can measure the angle by using the protractor, where beta 1 equal to 57. Okay, next draw the velocity, what we call velocity triangle, obviously diagram at the inlet of the stator. So the value of beta 2 already given, because the value given is the inlet relative flow angle. So the line that we draw based on the angle, we will obtain the relative velocity vector W2. Measure the line, so we will obtain the value of W2 equal to 57.4 meter per second. Use vector principle, so we can get the line for absolute velocity C2. Measure the line, the value will be C2 equal to 86.7 meter per second. And also we can get the angle for alpha 2, where the value of alpha 2 equal to 55 degree. Okay, so from the velocity diagram we know that the absolute velocity C1 equal to 55.4 meter per second, C2 86.7 meter per second, and the relative velocity W1 equal to 91.2 meter per second and W2 equal to 57.4. So for the x component, we know that from the question mentioned that we need to consider the constant axial velocity. So the x component for C1, Cx, and also the x component for W1 is equal. So Cx1 equal to Wx1 equal to 50. Similarly with the what I call the component, the x component for W2 and also C2, we'll get the same value. Cx2 equal to 50, Wx2 also equal to 50 meter per second. In terms of y component, so we can measure the y component for each C1, W1, W2 and so C2 vector by measure the line by referring to the y component vector. So we can measure Cy1 by referring to the velocity diagram. So Cy1 equal to 23.4 meter per second, Wy1 equal to 76.5 meter per second, Cy2 equal to 71.0 meter per second, and Wy2 equal to 28.7 meter per second. So these are the value for the velocity diagram for both at the inlet of the rotor and also inlet of the stator. Okay, for total pressure loss in rotor and stator, we need to refer to figure 2 that represent the graph that obtained by Howell 1942. And also we need to refer to the velocity diagram at the inlet of the rotor and also at the inlet of the stator. So data given for the rotor, we have alpha 1 prime equal to 45 degree, alpha 1 equal to 25 degree, and from the value we can determine the incident angle for the rotor. I rotor equal to negative 20 degree. By referring to the figures and also use the value that we obtain for I rotor, we can determine the value of omega bar, total pressure loss coefficient, where the omega bar for the rotor equal to 0.027 and the value also equal to delta P naught for the rotor divided by half C inlet rotor square, as shown by equation number 1. From velocity diagram, C inlet for the rotor actually is equal to C1 equal to 55.4 meter per second. And in order to obtain total pressure loss in rotor, we need to rearrange equation number 1, and then we can obtain the value of delta P naught rotor, which is equal to 41.43 Pascal. Okay, for the stator, data given for the stator, we have alpha 2 prime equal to 50 degree, alpha 2 equal to 55 degree. We can determine the incident angle for the stator. where I stator equal to 5 degree. By referring to the figure number 2 and also the value of I stator, so we can determine the value of omega bar for the stator. Omega bar for the stator equal to 0.024 equal to delta P naught stator divided by half C inlet stator square, represented by equation number 2. Okay, from velocity diagram, we know that C inlet for the stator equal to C2 equal to 86.7 meter per second. So for total pressure loss value in the stator, we need to rearrange the equation number 2, and then we can obtain the value of delta P naught for the stator, where the value will be equal to 90.2 Pascal. Okay, total efficiency. So we need to refer to the total efficiency for the equation. We need to refer to total efficiency equation, where we know that the total mu Tt equal to 1 minus delta P naught rotor plus delta P naught stator divided by H03 minus H01, or 1 minus delta P naught rotor plus delta P naught stator divided by U bracket Cy2 minus Cy1, represented by equation number 3. So from the velocity diagram, we can determine the value of U 100 meter per second, Cy1 23.4 meter per second, and also Cy2 equal to 71.0 meter per second. And from the total pressure losses value that we obtained in previous question, delta P naught rotor equal to 41.43 Pascal, delta P naught stator equal to 90.2 Pascal. Substitute all data obtained in terms of velocity diagram components and also total pressure losses into equation number 3. Thus, the total efficiency for the compressor stage is equal to 0.97 or 97%. Okay, to test your understanding for chapter number 5, part number 2, answer the question below. First question, what kind of losses need to considered for total efficiency calculation for a compressor stage? Question number 2, give brief explanation on how to manipulate graph that obtained by Howell 1942 for compressor efficiency determination. Question number 3, what is the importance of velocity diagram in terms of efficiency determination? Okay, so you have to answer the question by clicking the link provided in my blog. Remember that you need to know the password in order to open the link. The password was given throughout the video related to this topic. The clue is also given in the link. So that's all for part number 2, chapter number 5. Assalamualaikum.